In the last lecture, we introduced ourselves to the concepts of the Fourier integral and the Fourier transform. Let us quickly recall what we did. We observed that an aperiodic function of time can be considered to be a periodic function with a period going to infinity, and we found that as a consequence the function will have frequencies of all values extending from minus infinity to plus infinity, but then the amplitudes of the various frequency components will be vanishingly small, will in fact tend to 0. So, we will not have any meaningful data if we continue to take up the approach of evaluating the coefficients, Fourier coefficients, as we did in the case of a periodic function. So, we took up an alternative approach. We talked in terms of the coefficient density, which is the coefficient divided by the base frequency f naught, and the coefficient density turns out to be a meaningful concept in the sense that it does not vanish and it gives a relative idea of the different frequency component magnitudes. Coefficient density we also call the Fourier transform f j omega, and f j omega is in general a complex number, therefore it has got both magnitude and phase. So, corresponding to each f of t you have the Fourier transform f of j omega, and both f of t and f of j omega can be thought of as two different windows through which you can look at a function. One is a time description, the other is a description in terms of frequency. Both give equivalent information about the same physical phenomenon. We are used to observe a function as a sequence of values with respect to time. So, a function of time comes more naturally for us to visualize a physical situation of this sort. But imagine that you have an instrument or a creature which have got sensors receptive to different frequencies, different frequency bands. Then that particular instrument will observe the phenomena as in terms of the relative strengths of different frequencies. That will be in terms of the, for example, like Fourier transform f of j omega. So, let us now look at, once again, you have a function of time f of t, and correspondingly its Fourier transform f of j omega will have a magnitude f of j omega magnitude and a phase function phi of omega, which is an odd function. So, this is the magnitude spectrum, and this is the phase spectrum. We also observed that since both the magnitude and phase are essentially functions which are called for coefficient densities, if you take a small band of frequencies delta omega centered around a particular omega, this section of the spectrum, both the magnitude and phase together, will tell us about the idea of the strength of the signal at this frequency omega. In fact, these two sections represent a function of time which can be written as f of j omega magnitude e to the power of j phi e to the power of j omega t. So, this is the time function which is identified by these two sections of the spectrum. In other words, what we are saying is, even though there is a small difference in the frequencies in this band, if we assume that this entire spectrum represents a frequency component at this point omega at the center of this band, The time function corresponding to that is e to the power of j omega t, and its magnitude is the Fourier coefficient times of course delta omega. We must also have delta omega because this is f of j omega. I will write this again, f of j omega e to the power of j phi. This is the coefficient density, but since the coefficient density we are talking over a band delta omega, so it is delta omega over 2 pi because the density is in terms of the frequency e to the power of j omega t. So this is the signal that is represented by these two sections. This is the strength of the signal, this is the coefficient, and this is the time function. And if you take the limit of all such individual components over the frequency band just extending from minus infinity to plus infinity, this will add up to, that is from minus infinity to plus infinity, limit as delta omega tends to 0. If you take all such functions, this will be 1 over 2 pi minus infinity to plus infinity f of j omega, where f of j omega, now I am talking about combining f of j omega magnitude and e to the power of j phi together is a complex number f of j omega e to the power of j omega t d omega. That will be your f of t. So f of t can be thought of as 1 over 2 pi f of j omega e to the power of j omega t d omega. So this is the Fourier integral, and to get f of j omega from f of t, this is minus infinity plus infinity f of t e to the power of minus j omega t dt. So these are the two relations which are important in the Fourier transform theory. You can get f of j omega from f of t and f of t from f of j omega. We write these relations in more compact fashion in this manner. Fourier transform of f of t is indicated in this manner. A script f as a function of f of t, this will be the Fourier transform, this will be f of j omega. And to recover f t from f of j omega, we write this f of minus 1, this is the inverse Fourier transform, this will give me f of t. So this is called the Fourier transform. That is, you transform a function of f of t, function of time f t, to get the Fourier transform f j omega. And what you have here is called the inverse Fourier transform. We would also like to indicate these transform relations occasionally in this fashion. F of t and f of j omega form a transform pair. So we can indicate that functional relationship in this manner. F of t, arrow heading to f of j omega, this means in the forward direction you are doing the Fourier transform, and in the reverse direction you are doing the inverse Fourier transform. So as I mentioned, f of t and f of j omega are two alternate descriptions of the same phenomenon, and what we would like to do now is to find out the Fourier transforms for a few representative functions of time before we go on to a study of the properties of the Fourier transform. So to get some physical idea of how this f of j omega comes about for common time signals, let us work out a few examples, typical Fourier transforms. Of a few representative time signals. 1, suppose we have f of t as e to the power of minus at ut. I will call that 1a, let us say. A real quantity, a real, and a greater than j. That is, I have taken an exponential, a decaying exponential starting at time t equals 0. Ut is the unit step function. So it will be 0 up to time t equals 0 for negative values of t, f of t is 0, it starts at 1 and then decays exponentially. So, this is e to the power of minus 8. It starts 1. This is f of t. Now, the Fourier transform for this using the this formula that we had here will be f of j omega. You integrate this from minus infinity to plus infinity of f of t e to the power of minus a t u t dt. But since we know that f of t is 0 identically from t minus infinity to 0, I can start the integration from 0, go up to infinity. Strictly speaking, we should start from minus infinity to plus infinity, but from minus infinity to 0, f is 0. Therefore, I am starting the integration from 0. From 0 to infinity, the value of this function is e to the power of minus a t, and I have e to the power of minus j omega t dt. So, this will be e to the power of minus j omega plus a t, that is what is to be integrated. So, you have in the denominator minus j omega plus a, this should be evaluated between the limits 0 and infinity. Since we have taken a to be real number and minus k is a negative real number, when you t goes to infinity, e to the power of minus a t becomes 0 and e to the power of j omega t is something which oscillates between 0 and 1, I mean its magnitude at least. Therefore, e to the power of minus a t becomes 0 at t equal infinity. Therefore, the upper limit this is 0, at the lower limit it is 1, because when t equals 0 this exponent becomes 1. Therefore, result is this will be 1 over j omega plus a. So, e to the power of minus a t u t has a Fourier transform which is 1 over j omega plus a. So, how does its spectrum look like? So, f j omega equals 1 over j omega plus a. So, the magnitude spectrum will be f magnitude 1 over square root of a square plus omega square, right. Therefore, it will be something like this. And the phase spectrum as a function of this, all at a function of frequency. When omega goes to a very large positive value, the phase of this, the angle of this complex number becomes minus 90 degrees. That means it will go to asymptotically minus pi upon 2. And because the phase spectrum is an odd function of the omega, so it reaches plus pi upon 2 in the positive direction. So, that is what it is. So, this is the angle spectrum or phase spectrum, this is the magnitude spectrum. Now, even though we said that an aperiodic function has 0 amplitude signals at all frequencies, we still from the coefficient density we can see that the components of the signal at near our DC are stronger than the component of the signals at some other frequency. So, the spectrum gives us an idea of the frequencies at which the density is concentrated in this signal, the energy density is concentrated in the signal, because the components are more dense here than here. So, you can see the relative proportions of the different frequency components that go to build up the signal in terms of the Fourier transform magnitude, which is really the coefficient density. So, even though coefficients are all 0, the coefficient density gives us a measure of the strength of the signal at different frequencies. So, let us now continue this. Now, I purposely put this 1 a e to the power of minus a t, a real and a greater than 0, because I wanted to extend this idea and say that this particular formula that we had, f of t has a Fourier transform 1 over j omega plus a, will be valid even if a is a complex number. So, f of t suppose is e to the power of minus z t, where z is complex. Z, let us say, is a plus j b, and a is a real number greater than 0. Then the Fourier transform for that can be shown to be 1 over j omega z, which is 1 over j omega plus a plus g. So, this formula that e to the power of minus a t u t, here also you must have u t, has this Fourier transform 1 over j omega plus a, will be valid even if instead of a you have a complex number. The only requirement is that the real part of this complex number must be negative, because minus z, that is, if minus z is the coefficient of t, then the real part of that minus z must be greater than real part of minus z must be negative, or the real part of z must be greater than 0. The reason is, if you had an exponentially rising signal like this, for example, if you have, instead of this being negative, suppose it is exponentially rising signal, then this integral will not converge. This integral, when t becomes larger, will not converge. Therefore, you must have an exponentially decaying signal, then only it will converge at t equals by infinity. That is the reason why we had this restriction. Now, let us work out another example. Now, let us take a second function of time, a pulse function which is quite common and appears quite frequently in Fourier transform theory. So, we have a pulse of width d units, amplitude a. So, this is f of t. So, f j omega will be from minus infinity to plus infinity of f of t e to the power of minus j omega t dt. This is the standard form. In our case, this function of time lasts only from minus d upon 2 to plus d upon 2. Therefore, this can be written as minus d upon 2 to plus d upon 2, and in this interval f of t equals a. So, a e to the power of j minus j omega t dt, and that will be a e to the power of minus j omega t divided by minus j omega, evaluated between the two limits minus d upon 2 to plus d upon 2. And this can be shown, you can work this out, and this can be shown to be a d sin omega d upon 2 divided by omega d upon 2. That is the Fourier transform for that. So, this is the form sin theta by theta type of variation. So, the spectrum for that f of j omega can be plotted in this fashion. Like this, where this at the DC, the Fourier transform will be having a value a d, because you recall that sin theta by theta will have a value equal to 1 when theta equals 0. So, this will be a d, and then it oscillates, but with diminishing amplitude. Now, when does the first 0 occur? First 0 occurs when sin omega d upon 2 is 0, that is omega d upon 2 equals pi. Therefore, the first 0 occurs when omega equals 2 pi upon d. In fact, this is the spectrum which we plotted yesterday in the last class when we talked about the evolution of the Fourier coefficient density starting from a periodic pulse train. This is exactly the type of spectrum that we plotted. Now, since f of j omega happens to be real, I do not plot the magnitude spectrum and phase spectrum separately, because f of j omega is real, it is either positive or negative. So, I can combine both the phase and magnitude information into one plot like this. However, if you wish, you can plot the magnitude spectrum separately like this. This is f of j omega magnitude, and the phase spectrum will be, whenever this is negative, you can say that is minus pi upon 2 minus pi. So, this minus pi, and then you can write this as plus pi. So, this can be considered to be the phase, and that could be the magnitude. So, this is an alternative way of depicting the spectrum, both phase and magnitude, but when the Fourier transform is real, there is no point in doing this separately. We may as well exhibit the entire f of j omega being a real function of time, real function of omega in one plot like this. Now, let us have a little bit of diversion here. We know that sin theta by theta curve, which occurs frequently in Fourier transform theory, will be like this. This is 1, this is pi, 2 pi, 3 pi, this is minus pi, minus 2 pi, etc. Now, there is another function which is called sinc theta or sinc x. Sinc x equals defined as sin pi x over pi x. This is in the literature, the sinc x is a term, is a function that is defined as sin pi x over sin pi x. Therefore, if you plot sinc x as versus x, it will be similar to this, because when x is 0, both the numerator and denominator is sin 0 by 0 type of thing. So, it will be 1 and it will have oscillations, but the 0 occurs whenever sin pi x is 0. That means, for integral values of when x is equal to 1, 2, 3, 4, the sin pi x becomes 0. That means, the curve will be something like similar to that, but what we have now here is this will be 1, this will be 2, this will be 3, this will be 4, this is minus 1, minus 2, minus 3, minus 4, like that. So, occasionally people prefer to use the sinc function instead of sin theta over theta. You can have a compact expression sinc x, which is will be the value of sinc x will, as a function of x, will vary in this fashion. So, we can write this, if you like, as AD sin omega d over 2 pi times 2 pi over, oh, I am sorry, sin omega d upon 2 pi times pi, right, times pi divided by omega d upon 2 pi times pi. So, we can write this therefore as AD up times sinc omega d upon 2 pi. So, AD sin omega d upon 2 by omega d upon 2 can be written as AD sinc omega d upon 2 pi, and the sinc function vanishes at integral values of the argument when x equals 1, 2, 3, 4. So, at what values of omega will it will become 0? 2 pi upon d, 4 pi upon d, and so on and so forth, 2 pi upon d, 4 pi upon d, 6 pi upon d, etc. So, this is an alternative way of writing this. So, this function, this pulse function, sometimes called a gate function, because it has a non-zero value only between these two limits. A rectangular pulse function has this Fourier transform AD sinc omega d upon 2 pi. This sinc function tries to normalize the values in a nice way, because you are now having integral values of x, and this will become evident now if I take a second example where you normalize the pulse so that you have unit amplitude and unit duration. That means this is minus half, this is half, this is t, and a equals 1. This is f of t. So the Fourier transform for that, if you go back to our old formula, AD sin omega d upon 2 by omega d upon 2, A happens to be 1, D happens to be 1. So AD is 1 sin omega D is 1. This is A is 1. So omega d upon 2, d is 1, therefore this is omega upon 2 divided by omega upon 2, which if you like to put this in terms of frequency, this is sin pi f, omega being 2 pi f, this is sin pi f, therefore this is sin pi f, and this is indeed sinc f. So consequently, a pulse normalized to have unit amplitude and unit width will have a Fourier spectrum which is given by sinc f. That means if you plot the frequency f of j omega, but in terms now f of the frequency, and if you graduate the x axis in terms of frequency, you will have this is 1, f is 1, 2, 3, minus 1. So what this does is sinc function only tries to normalize things. If you have a normalized pulse, unit amplitude, unit width, then the Fourier spectrum will be like this, unit height, and going to zeros at 1, 2, 3 cycles per second. Okay. So this is just a special case of this, because once you normalize, you have a sinc function which is surprisingly a very simple function, sinc f. Let us now work out a third example.